Alright, so in the previous video we introduced the idea of using the series method to solve differential equations. And in this video I'm going to show you an example of how to implement this method to solve this very basic first order differential equation. You might have seen a form of this in the first few videos of this series because this is a separable first order differential equation. And we saw that by solving it we actually obtained the following solution, which is essentially just a constant times the exponential function. So it is an exponential growth function from elemental principles. So the series method consists of assuming a solution of an infinite sum or an infinite polynomial, and we're going to substitute that solution into the differential equation and then expand the terms and then group them according to the power of x. So let's do that here now. We know that the first derivative from the first video, it's going to be m equals to 1 of m times am times x to the power of m minus 1 minus, so this is going to be another sum. It's going to be m equals to 0 to infinity am x to the power of m, and that's all going to be equal to 0. So we have our series form here. Now we're going to expand each of these sums up to 3 or 4 terms, and then we're going to start grouping them together. So what's going to happen in this one? We're going to have m equals to 1, so that's going to start from, this is going to be 1, this is going to be a1, and I'm just going to use brackets just to show you how, just to differentiate between the two sums beforehand. And this is going to be a1, 1 minus 1 is 0, so that's just going to stay like that. The second term in this series is going to be m equals to 2, so that's going to be 2, a2 x to the power of 2 minus 1, so that's just 1. And then the next term is going to be a3 times x to the power of minus 2, sorry, x squared, plus a whole bunch of other terms. Now for this sum, we're going to have what? We're going to have a0 plus a1x plus a2x squared plus a whole bunch of other terms, and all of that is going to be equal to 0. So what we're going to do now is we're going to start grouping terms together, so and depending on which powers of x they're multiplying. So in this case we can see that this term and that term are not multiplying x at all, so they should be grouped into one. So we can group them like this, a1 minus a0. So that's going to be the first group. The second group is going to be this one, because that's multiplying x to the power of 1, and this one. So we're going to write this as 2a2 minus a1 times x, and the third group is going to be these two, so that's going to be plus 3a3 minus a2, and all of this is going to be multiplying x squared, and that's going to keep going, and we're going to set this equal to 0 on the other side. So the idea now is that because this is a polynomial and it is an infinite sum, each of these groups should be equal to 0 so that this condition is satisfied. So if we want the left hand side to be equal to the right hand side, we need to make each of these groups equal to 0. Now we know x shouldn't be 0 because that would be a trivial solution, and having a solution y equals to 0 is really ridiculous and not very useful. So the constant terms need to equal 0 somehow. So the first derivation that we can make is a1 equals to a0, because a1 minus a0 should be equal to 0, so we're just moving the terms around, and that's what we're going to get. The second group is going to give us the following: 2a2 should be equal to a1 for this condition to be satisfied, and then we can make a substitution here, so we know a1 is equal to a0. So this leads to a2 in terms of a0 is just going to be a0 over 2. And for the third group, we're going to have 3a3 equals to a2, and we know a2 is just a0 over 2. And now we solve for a3, so that's going to be a0 over 6. And you can immediately see that some pattern is emerging from this. So what we want to do is we want to express a sum of terms that are just the coefficients from m equals to 0 all the way to infinity. So in this case we're going to have a0 plus a1 plus a2 plus a3 plus all the other terms. So we're just going to start making these substitutions here. So what's a0? Well, a0 is just going to be equal to itself. a1 is going to be equal to a0, so that's going to be a0. a2 is going to be equal to a0 over 2. Then a3 is going to be equal to a0 over 6. And that's going to keep going. And what is the pattern that we notice here? Well, we can see that the denominator is sort of following a factorial that is increasing from 0 to all the way to infinity. So let's see if we can write this as a0 over 0 factorial plus a0 over 1 factorial plus a0 over 2 factorial plus a0 over 3 factorial plus all the other terms, and it does actually fit this series. So we can infer that all the other terms are going to follow the same pattern, so that this particular sum is going to be equal to a0, so that's the leading term here, times the sum to infinity of m equals to 0, and that's going to be 1 over m factorial. So that's a very interesting thing. So now that we have expressed this sum as a function of a0 alone, we can actually substitute it back into the original solution that we had. So I'm just going to go up here. So this essentially means that I'm just going to make the eraser a little bit smaller. This essentially means that this particular sum is going to become the following. This is going to be a0 times sum m equals to 0 to infinity of 1 over m factorial times x to the power of m. So that's going to be our general solution to this equation. Now, what's this going to be equal to? Well, this is going to be equal to a0 1 plus x squared over 2 plus so forth all the way to infinity. And we can notice immediately, so this is going to be equal to a0 times the exponential function, because this series here, if you have investigated some infinite series in the past, you would know that this series here corresponds to the exponential function. So we have obtained the exact same solution as we did using separation of variables, where we obtain y equals to a e to the power of x. So this is just to illustrate the power of the series method for solving differential equations. But the main issue is that you would have noticed that this method is very, very rigorous. And we don't usually implement it for practical problems. There are much more efficient methods that we can use, because most differential equations don't have analytic solutions anyway. And even if you use this method, what you're going to end up with in most cases is just an infinite series with some pattern. So that's not really going to be very useful unless you take out some of the higher order terms in the series and then investigate what it looks like when you take a limited number of terms in it. So I'm just going to conclude this method here, and then in the next few videos we're going to move on to a more practical method called the Laplace transform method for differential equations.